Okay, let's finish our discussion about plate boundaries. I had to crop the last video, got a little too long there, so we're going to start a fresh one here with our final type of plate boundary, which is known as the transform boundary. So a transform boundary is when the plates are sliding past each other. Let me give you like a live view of this. Here's an example of a plate of a transform boundary, sort of a live view right here. And let me start it going. Notice the plate on the left is moving toward us, the plate on the right is moving away from us. This mountain range is being split apart like this. Okay, very interesting. Okay, this one does produce a lot of earthquakes. Not the most powerful earthquakes, not as powerful as the earthquakes at a convergent boundary, but they can be pretty powerful. All right, so let's take a look. This is what you see right there, the two plates moving. So here's what I want you to do. This is the symbol on the map with the arrows going past each other like this. What I'd like you to do is I'd like you to go to the ESRT and find the only named transform boundary on page 5 of the ESRT. There's one that has a name. Please find it, record your answer right here. Let's see how you do. And your answer was the San Andreas Fault, right here. There it is. The San Andreas Fault is what produces all those earthquakes in California. There are a couple other transform boundaries out there, naturally. There's one down here by the Scotia Plate, and there's one down here by the Sandwich Plate. And, you know, there's one here in New Zealand right there. Okay, so they're not rare, but this is the most famous one right here. It's the one that's got a name right there, the San Andreas Fault in North America. And what's interesting about this is from what they say, you know, people always say, oh, well, California's going to fall off into the ocean. That's not what's happening. One piece of California is sliding north, while another piece is sliding south. So one day, Los Angeles and San Francisco might be right next to each other. So let's take a look. That's your transform boundary. So the example that you should have put before was the San Andreas Fault. Okay, so now let's take a look at what's causing this plate motion here. Why is the plate motion happening? Now, I'm going to move to the next page because I've made some updates and your diagram does not look like that anymore. So now let's go down here to what your diagram looks like. Your diagram looks something like this. And I'm going to make it a little bit larger for you. Okay, now this diagram corresponds to page 10 of the Earth Science Reference Table, so we need to look at page 10 of the ESRT while we look at this. Okay? So we have to compare that diagram to this diagram on page 10 that we know so well. So I need to be looking back and forth from this to this. From this to this. And try to get a feel for what's the same and what isn't. Alright, well, first, we have our lithosphere on top. This is the lithosphere. Feel free to label that. Now, right beneath the lithosphere, we have the asthenosphere. And beneath the asthenosphere, we have the stiffer mantle. Right down in here. Now what happens is tremendous heat comes out of the inside of the Earth. Tremendous heat. And that causes the material in the asthenosphere to circulate. And we call this circulation convection. We should know this, you know, from earlier in the year. We've seen it in weather. We've seen it in a lot of things. You could see it in boiling water. But what happens is this material gets very, very hot, and this superheated material tends to rise. And it will spread right here. Okay? That spreading is going to help move these two plates apart right here. All right? So, let's continue. This material is going to continue. It's going to lose heat eventually, become more dense, and it's going to sink and then circulate back again. All right? So what happens is, round and round we go with a convection cell, like this. Okay? So we have to assume there's another convection cell on this side doing the same thing. Down it goes. And this material continues to move in the direction it was moving, loses a little heat, becomes more dense, and sinks. And then continues back and forms that convection circulation that we're familiar with. And again, we have to assume there's a different convection cell over here, like that. And you can take a look and see the exact same thing in your ESRT on page 10. Notice the circulation pattern right here in the asthenosphere where the material can move. That plastic mantle, that material can move. See the circulation right there? Okay, so what's happening? Where the material sinks, that's where the plates are coming together, right here. So notice this whole plate's moving this way. Now what happens to the plate? The plate moves, and the plate subducts into the earth like this. Scientists now realize that it subducts much more than they originally thought. In fact, they think it actually goes all the way through the asthenosphere and begins to melt down here near the stiffer mantle area. So this subducting goes far deeper than we thought. So the plates are moving the same direction that the material beneath it is moving. So if you want to know which way the plates are moving, just look at the direction the material is moving beneath it. So where the material converges and sinks, that's where you have the plates converging. Okay, so let's put this into some language we can remember. So your hot, less dense material, right here, comes up from deep inside the Earth's mantle and it rises. When it cools near the surface, it's going to get a little more dense and it's going to sink. It's going to get a little more dense, going to sink again. This resulting convective flow, I'm showing it for you here, this convective flow in the mantle is what pushes and pulls these plates around. Okay? Now, some scientists are trying to debate whether it's the push that's happening here or whether it's the pull of this heavy thing sinking and pulling everything down with it that has a greater effect. I say, what does it matter? The two are working together. There's pushing here, there's pulling here. The plate is being guided this way by the movement of the material beneath it. So one day when the inside of the Earth eventually cools down, this plate motion will stop, but that's billions of years from now. Okay, so let's take a look at an animation that's going to sort of summarize our plate tectonics right here. And this is another good one. Now check this out. So first, let's get a feel for what's happening. Here we have a mid-ocean ridge, and look at the arrows. So what type of boundary is being depicted right here, where I'm showing right now, by this ridge? Hopefully you said it was a divergent boundary, and you'd be correct if you did. Now here, this plate is sinking beneath this plate, right here. See that arrow? See this arrow? So what type of boundary is right here by this deep oceanic trench where this subduction is occurring? What kind of boundary is that? And your answer is that that would be a convergent boundary where the subduction is happening down here. All right, and now notice that the melting subducting plate melts the rock above it even, and it produces a volcanic mountain range right here. Okay, and notice this is a little hint here. As we get farther and farther away from the ridge, the rocks get increasingly older. That's review. And let me start the animation going for you. There it is. Now, look at this. What kind of boundary do you see right along here? Look at this. And right in this area. That's a transform. Transform right there. Sort of sliding past each other. That's the reason why you have earthquakes out here. See that little break right there? That's a transform motion. Okay, everyone, I hope this is all really clear. Let me just play this one more time because it's really that good. All right, examine every bit of it. And one more time. Volcanic chain. Okay, this looks sort of like what we saw on the ESRT. Right here would be the Nazca plate. Here would be your South American plate. And here's a mid-ocean ridge. All right. I hope it's all really crystal clear to everyone. Thanks for paying really good attention. And ask any questions at the end. Have a fantastic day.